Hi, I'm going to walk you through the page or the PDF that is called the Taylor Series Summary. And you will see that in question number 1, I have a few annotations about the directions for clarity. So the directions as stated say write the Taylor series, I really mean the Taylor series centered at x equals 0. So some of you are going to say, isn't that a Maclaurin series? And I'm going to say, yes, of course it is, but it is also a Taylor series, since Taylor is the broader name. So write the Taylor series centered at 0 for each function, including the first 3 non-zero terms. So if one of the terms, like if the x to the first term zeroes out, you don't get to count that as one of your 3 terms. So write out the first 3 non-zero terms and then write the general term. Now, sometimes in AP created materials, they will write out term, 3 terms, dot, dot, dot. They'll have a generalized term and then dot, dot, dot. And then they'll have sigma notation. I personally find it easiest to write out the first 3 terms, ignore the idea of writing a general term in the midst of things, because you will have some questions about, oh, wait, am I starting at n equals 0? Am I starting at n equals 1? And I feel like that lack of clarity can just be avoided by jumping to the sigma notation. It is more precise and I would argue just better, overall, just better. So these are ones that I certainly hope that you have committed to memory through your use of them in this unit. If that is not the case, no time like the present. And I will warn you that future you, i.e. you in the 3rd quarter going into 4th quarter, when we are doing our spring unit with series, when we're getting ready to take the AP exam, you of the future is going to be so happy if you commit these to permanent memory now, not just memory for the next assessment, memory for forever, okay? So just try to see if you can manage that. These all are patterns, and patterns should stick in our heads more easily. So this endeavor today is going to involve a lot of you pausing and then coming back in order to do this the way that I hope that you will. So I would invite you now to please pause and try to write out those 5 series in the way that I described. First few terms, and then the general term. Actually, maybe we should do the first one together, just so you know what I mean for sure by the directions. So e to the x is the Taylor series 1 plus x squared over 2 factorial plus x cubed over 6 factorial plus, you might remember this from the discovery lesson that we did together, where we have, oh, I didn't mean 6 factorial, heck, I meant 6. Sorry, 3 factorial is 6. Okay, sorry about that. So you might remember that in our discovery lesson, we had 3 times 2 times 1 there. Remember that whole conversation? Okay, so that can help you remember the pattern, right? And then dot, dot, dot. And like I said, you might see some materials where they write a general term here, kind of, and then a dot, dot, dot. I don't love that. I used to do that because I saw it a lot in solution manual type materials or on Calc Chat, and I think it is the opposite of adding clarity. It subtracts clarity. Okay, so then that would be my general pattern, right? Where did the derivative part go? Okay, hopefully you know the derivative of e to the x, every single derivative, every 3rd derivative, 4th derivative, 5th derivative of e to the x at 0 is going to be 1. So you don't see that per se because the 1 is there, but not important to write. Okay, remember that sine is an odd function, cosine is an even function. That might help you with the next 2. Okay, now for sure, actually pause and write the other 4. Okay, I'm going to stay on this slide just a little while to make sure that you can check all your answers, but as I'm doing that, I'm also going to talk to you. All right, so for sine, the way that I keep this in my head, guys, if you're having a harder time memorizing, I know I'm not a great memorizer myself, and so I try to pass along my hints because that is challenging. So think about the fact that you're centered at 0 here. Sine of 0 is 0. So the constant that you're going to begin with is 0. So that's not going to count as one of your non-zero terms, obviously. And then since sine is an odd function, you see the odd powers show up here. It's because of math, right? Like the symmetry of the sine function is that it's rotationally symmetric around the origin. That's what an odd function is. And then the odd terms of a polynomial have that feature as well, right? Or the odd powers, I should say, of a polynomial would have that feature as well. So you're going to start out with an x, and then you're going to alternate, okay? And so notice that in all of these representations, the first term that you have is positive. And if there are alternating signs, then it goes positive, negative, okay? Notice also that, like, it's just like always, right? All of these Taylor structures, like this is a 3, this is 3 factorial, this is 5, this is 5 factorial, okay? Now, to go from there to the generalized form, there are just some things you have to like put into your mind, okay? The fact is that to represent odd numbers, you're going to say, well, an even number is 2 times an integer, and then adding 1 is going to make it odd, right? Think about the number line and how odds and evens alternate, right? And so if I'm adding even 2 times something, if I were off by 1, that is then going to bring me to an odd. Okay, so whatever your exponent is, that has to be the same as your factorial representation down here, and then this part is going to be your sign alternator. You could potentially write this with starting from n equals 1, and that would then change what you have in these positions, and it might still also be a right answer, but let's just stick to having one right answer. I've thought about like trying to explain that, but if you think you have something that works, and you have n equals 1 at the bottom, that's just fine, okay? Make sure that it does work by plugging in a few terms and verifying that you do have something that makes sense, okay? For cosine, again, think about how cosine at 0 equals 1, and that's why there's a 1 here, okay? For the same reason that up above, sine at 0 is equal to 0, and that's why you don't have a constant here. Okay, so this is going to start at 1, and then cosine is an even function. So you have the even exponents. And then the same kind of thinking that I was discussing for sine works here. These are the evens, right? 2 times something, 2 times an integer makes it an even. Okay, this natural log one is the one that I had the hardest time remembering. I think it actually maybe just comes up the least in the kinds of problems that I write. Maybe my own like personal bias against like knowing this. But natural log at 1 is 0. So if I plug in 0 here, right, I end up with natural log of 1. Natural log of 1 is 0. Think about your natural log function. That point is 1 comma 0, right? So that's how I know that natural log of 1 is 0. Other ways to know it too. Then the thing that's interesting about this particular Taylor series is that it's the one where the factorials cancel out. So you just have the actual numbers here, no factorial. The other terms cancel out, and you should have seen that in problems that we've done already, okay? The last one, you're going to think of this, hopefully, this is the way I think of it anyway, as being related to this formula, right? Like a geometric, this is a power series. It's a power series with the first term of 1 and a ratio of x. So you're just multiplying by x, right? Which is why the signs don't alternate. There's nothing else with factorials. Just think about it that way. It's a little bit different than how I think of the other ones, okay? So those should be all things that you have. The next part is so cool, okay? So notice that in each of these statements, we have take a derivative, okay? That's a symbol that means please take a derivative of the thing. All right, so I would start out here by saying, okay, I want to take the derivative of e to the x. And so my e to the x statement, here's my symbol for take the derivative, and I'm going to replace e to the x with that polynomial or that Taylor series that I wrote out earlier. And so on. Okay, so now if I take a derivative, I'm going to just go term by term. That is the joy. That's the whole reason that we are excited about Taylor in the first place, is that polynomials are easy to differentiate. It's fantastic. Okay, so the derivative of 1 is 0. The derivative of x is 1. The derivative of 1/2 x squared is going to be x. This is 1/6 x to the third. So the derivative of that is 1/2x squared, and so on. Now, hopefully you recognize what I just wrote in red. What is that? It is itself e to the x. So we just showed using Taylor that the derivative of e to the x is e to the x. So that's why I'm saying it's expected results, but they're awesome because you're showing, like you're proving that these derivatives are what we memorize them to be, okay? So this is a moment for pausing again. I would like you to do similar work. Take the derivative of sine. You know you want to take the derivative of, then in place of sine, write out the Taylor series representation and then think term by term. How would that derivative work? Pausing. All right, so here's some work to talk about. We already discussed e to the x, so with sine of x, you can see in blue, I wrote, I'm taking the derivative, and then here is my sine, right? Here I am writing out the Taylor series representation of sine. And then in the next line of work, I'm saying that is equivalent to, that's my equal sign. If I take the derivative of x, I get 1. If I take the derivative of this term, that 3 comes down in front, the exponent goes down by 1, and 3 factorial means 3 times 2 times 1. So you can see that these 3's cancel. This leaves me with x squared over 2 factorial as that term. In the next bit, same idea. The 5 is going to come down in front. My exponent's going to go down to be a 4. My 5 factorial is 5 times 4 times 3 times 2 times 1. Short way to write that is 4 factorial. The 5's cancel. Now, if you look at these terms, 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus dot, 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 dot. What is that? Hopefully you recognize that to be cosine. Is that what we would expect? Of course, because the derivative of sine, right, derivative of sine is cosine. So that is the expected yet awesome results. All right, I do not know how much detail I should go into here. All right, but here is my pre-written out work, finding the derivative of cosine and getting the opposite of sine. All of the pluses and minuses reversed, but otherwise it is the sine function. And then taking the natural log of 1 plus x and taking its derivative and getting 1 over 1 plus x. Now that is interesting. You may or may not remember that the derivative of natural log of a thing, now I'm using the letter u here. U is understood to be a function of x. That's my own abbreviation. So a function of x means blah, blah, blah with x in it. And the derivative rule for that is 1 over the thing times the derivative of the thing. This last part is because of chain rule. So if I look at this, its derivative is 1 over the thing, 1 plus x, and the derivative of 1 plus x is 1. So there's not really a chain rule piece to be super aware of, okay? So that's that, okay? Now I do think recognizing this, I was telling you earlier that I have a harder time remembering the Taylor series for this. This fact helps me. There are times that I work kind of backwards to figure out what it is that I'm kind of having a hard time remembering, okay? And so note that I knew this last part, this being equal to this. This is because the series that I just put a box around, that's geometric with my constant ratio of negative x, right? I'm thinking again of this formula. Okay, and if your ratio is negative x, you're going to end up with 1 minus negative x, which is 1 plus x. Okay? Oh, so cool. Math is great. Okay. So now, like I said, this is a review page, and so I'm going to be alternating now between having you pause and looking at solutions, okay? I'm not necessarily going to be writing out actively with you a lot of this work. If you do struggle with this content in any way, shape, or form, please, I beg of you, reach out to Mr. Covey or to me. We definitely want to help you, okay? So this one starts out, find the first 3 terms and the general term for a series for that. Now, there's a painful way you can do this, which would be to calculate a bunch of derivatives and use the general Taylor series. But what I see in here is my good friend e to the x. So I recommend that you start out with what does e to the x equal as a Taylor series. And then do algebra. Subtract 1, divide by x squared on both sides of the equation, and you'll be good to go, okay? I'd like you to pause and try. Okay, let me walk you through a solution. So the first thing I did was to write out the Taylor series for e to the x. It contains a 1. So I can see in the statement of the question over here that I have a -1. So I'm going to subtract 1 from both sides of the equation, which would yield this, right? Just subtract the 1 over. And then the other piece that I need to pick up is dividing by x squared. So I'm going to divide on both sides of the equation by x squared. Now my writing is a little messy here because I just was trying to fit everything in it without having to scroll. I hate scrolling. So you can see here that I just took this equation, and what I was thinking about was dividing on the left side by x squared, so that's this, and then dividing every single individual term by x squared. So this term divided by x squared, this term divided by x squared, this term divided by x squared, right? That's how I was thinking. And then I did clean that up, and that's the part that's squished in here in blue because I was trying to make it fit. So this top line in blue, that I will indicate right now with a box, that was just thinking term by term by term, dividing by x, and then I tried to write that into general form, right, because it asked for a general term. Now, if you decided to write this starting from n equals 0, your series representation, your sigma notation, I should say, will be slightly different, but just make sure that it works, right? Plug in a few terms, right? Plug in 0, plug in 1, plug in 2, and make sure that you get what I have in the red box. If you do, you're good. You can have a different correct answer, okay? All right, so the next bit is very similar to what we just did. So use algebraic manipulations to find a series for each function, and then write the sigma notation. So within each of these, you're going to start with a classic Taylor series that you already know, something that's centered at 0. So for instance, in this first guy, what do we know about e to the x? Let's think about that. So here's my e to the x. And now I really want e to the 2x. Well, let's first think about e to the box. X and box, right? They're kind of the same. Back in elementary school, you would do problems like this all the time. You'd fill in the box. Oh, that's 2. I'm smart. Okay, but then problems become this. And you solve it using an algorithm, but it's the same thing, you guys, right? Fill in a box, find what the value of x is. Really the same. So box math is really just a variable. So if I were to go through my e to the x and write e to the box, it's this. So in this problem, I need this. So here's my box. Remember that this box implies parentheses. Okay, and that's your starting point for finding the e to the x portion, and then you need to throw in multiplying by x. Okay, same ideas for, related ideas for the next one. You're going to write out the sine Taylor polynomial, divide each term by x. In C, you're going to take the cosine Taylor polynomial, you'll subtract 1 from it, and then you will multiply every term by x squared. Okay, please try by yourself. I expect that you pause. Okay, looking at my solutions that I wrote earlier, now maybe some of these have some small jumps in them. So again, if you feel uncertain about something, definitely talk to your teacher. Okay, so here is the result of my plugging 2x into the box, so to speak. I did choose to, at that point, write it in a generalized form over here, and that is just the e to the 2x portion. So now if I multiply every single term by x, I'm going to have an additional x. So if I have 2 to the n and x to the n as a format of every single term, and then I have an additional x, you can see by properties of exponents, x to the n times x to the 1, you add the exponents when you're multiplying. So that is where my sigma notation comes from here. Is that the only way to write it? Absolutely not. One small variation that comes to mind would be just writing it like this. That is fine, starting from n equals 0. Right? If you have that, that's okay. What else, right? So again, I cannot go through every possible correct variation. If you're not sure if your variation is right, talk to your teacher. Or write out a few terms, test it. Okay, the next one, I did not write out all of my work on this, so that's what I was saying, maybe my work is a little sketch, but I just thought about how the general sigma notation looks for sine, and then I said, okay, if I were dividing every term by x, that means the exponent on the x has to be 1 less. And so my normal exponent would be 2n plus 1. If I take away the 1, if I make it 1 smaller, then I just have 2n. So there you go. Okay, that was like an expedient way of doing it. If you have more writing, totally legit, that's fine. Okay, so cosine of x minus 1 is the same as having our entire cosine function without the 1 in the front, right? Usually we have a 1 right here. We don't have that, okay, because it's the 1 is subtracted over. All right, so then I did go ahead and try to write that in generalized notation. You wouldn't necessarily have to do that at that point. You could take every term of that and multiply through by x squared, term by term by term. But in any case, your sigma notation needs to represent that the x squared is there. So the exponent on my x went up by 2. I wouldn't have to have this all smushed together. I could have x to the 2n times x to the second within my sigma notation. That is completely fine. And then have my sign alternator out here on its own. Okay, that's the same thing with the sigma, et cetera, et cetera. Okay, all right. This one, oh, classic. Okay, this limit is something that you learned and I believe committed to memory during math analysis. And what's so great now is, especially for those of us who have a kind of lousy, just rote memories, is that this allows you, knowing Taylor series allows you a backup. Right? Another way to be like, oh crap, you know, like if you're having that moment, you're like, I don't remember if this is 1 or negative 1 or 0, it's one of those, right? If you're having one of those times, then what you can do now is to be like, okay, I'm going to write this out. Here's dividing by x. I'm going to put the Taylor series up on the top. So fill in the Taylor series for sine, and then think about dividing by x, and then think about taking the limit. Okay, time to pause. Okay, so at the top of this, you can see in my work that I just wrote out what sine was. Then if I go through taking the, this is actually what the question was, this part here, okay? And so now if I go through and I just term by term by term, divide by x, I get 1. Divide by x, the x cubed becomes x squared. Divide by x, the exponent goes down by 1. Right, if I just do that term by term by term, and then think about the fact that I'm taking a limit as x approaches 0. Every term in here, which is all of them except the first term, every term in here is going to zero out because x is approaching 0. So that just leaves me with the 1, which is the limit that you memorized back in the day. As x approaches 0 is 1. Caution. One of my favorite questions to ask on a final. I'm such a jerk, just in case you didn't know that already. This was one of my favorite questions to ask back when I taught Calc AB. And kids would fall for this just right and left and say that that was 0. It's not, or say that that was 1, excuse me. It's not this expression that equals 1. It's the limit, right? This function, as you get closer to 0, is approaching the y value of 1. And it's, well, it's for many reasons, but we see one reason right here. Okay, I'm rambling. I'm sorry. Okay, let's move on. Okay, this question is kind of like what we did in number 3, so I'm not going to really talk about it much. I'd just like you to try it and come back for the solution. Please pause. Okay, here we are for our solution. So 1 minus cosine. Notice on the right-hand side, I wrote 1 minus, and I used brackets, and I inserted the Taylor series for cosine. I need to be a little cautious about my plus and minus signs moving into the next step. Then the next thing I'm going to do is to take care of the little simplifying, right? 1 minus 1 is not there anymore, 0. And I'm going to take care of my pluses and minuses. And then in red, you see that I'm taking care of the dividing through by x squared. So term by term by term, my exponents are going to go down by 2 because I'm dividing by x squared. Now I'm bringing it back to the question that actually was presented. So the limit of this expression is going to be the limit, and then within these brackets in black, I have the result of taking term by term by term, dividing out the x squared. So all of the exponents are down by 2. And then notice that all of the terms except one of them contain an x. So all of these terms throughout all the way down here for, going on forever contain an x. So as x approaches 0, they're all going to 0 out. The only thing that remains is 1 over 2 factorial, which is equal to a half. So that is my limit. Isn't that cool? It's such a great way to find a limit, right? I love it. Okay, number 7, again, a problem for you to try on your own. So in this problem, we do, the way that I approached it was through finding some derivatives. And I think maybe that's my own, yeah, I think that's what I want. That is what I want to have you do. Okay, so I'd like you to start out. This is going to be a longer problem in terms of time. Okay, start out with your function that is natural log, and then find a derivative, find a second derivative, find a third derivative. So let's start it together, actually. This is 1 over x, which is x to the negative 1. So the next derivative would be negative x to the negative 2. Then positive 2x to the negative 3, okay? You need to find a couple more because I was really just mean, apparently. We're going to find the 4th derivative and the 5th derivative, okay? Then you're going to be centering this at 1, so you need to evaluate each of these statements at 1. And so forth. And then use the general structure of your Taylor polynomial to come up with your answer. Actually, this question is related to the last question that you have. So why don't we do both of them before you come back, okay? So find the Taylor polynomial and then use that Taylor polynomial to estimate the function value at 1.2 to 4 decimal places, which will happen by virtue of what I'm asking you to do previously. Okay, so this will be our last pause, and then you'll come back and see the last 2 answers. Okay, so the values that are highlighted in yellow are what you should have accomplished through taking the derivatives and evaluating each of them at 1. So those are going to be my derivative values in my Taylor polynomial. If you look from there down to my writing here in blue, this is the general structure of my Taylor polynomial. So I haven't filled in any specifics here yet. This is, just saying like, here's the function value, then derivative over factorial, x minus 1 to the 1, derivative factorial, x minus 1 to the 2, and so on. That's what I'm substituting into. And then my value, so here's my 0, that's right there. Then coefficient of 1, right? This term is this bit. This term is this bit, and so forth down the line. So my answer is this thing that starts out, the line that starts out Taylor polynomial of degree 5. Okay, so that whole long thing. Okay, then if you utilize that to try to estimate the function value. Okay, first of all, why am I saying estimate? Well, if this went on for infinity, right, if I had an infinite number of terms, then what I have here would be like what I would have if I had an infinite number of terms would be exactly equal to this function natural log of x. However, I do not have an infinite number of terms. I stopped at degree 5. So this is an estimator of natural log of x. So if you think back, like historically in math, this was such an epic thing because back in the day, they didn't have the TI-84 or Desmos to pull out and just type in natural log of something, right? This was the tool. This is what allowed mathematicians to calculate these things. It's amazing. So if they wanted to have a pretty decent estimate, really decent estimate of natural log of 1.2, guess what they did? This. They took their fifth degree Taylor polynomial, they substituted in 1.2, and that's why the centering at 1 was really nice, right? If I want to find natural log of 1.2, I'm not going to center it at 5. I'm going to center it at the closest nice number, right? The closest integer, perhaps, right? And utilize that. So 1 is close to 1.2. If I want natural log of 1.2, this is the guy I might pick, right? And then all of these values here, you can choose to be old school and do this without a calculator and see how it feels, but I won't even make you do that because that seems a little cruel. So get to this point, and then if you throw it on your calculator, you do actually get a very precise decimal. And that is amazing. Think of doing math by candlelight, right? Back in the day. And it's just amazing that this is something that could happen. Humankind is amazing, you guys. Inventions happen. Things get figured out. Okay, we are at the end of our fall unit on series. This is a list, if it helps you, of things to study. So feel free to pause if you need to look at this longer. Otherwise, I wish you a fond adieu.